Alright, so I wanted to show a sort of simpler form of the quadratic equation, which explains a lot of crap that's happening, right? So, yeah. So, given a parabola, a times x squared plus b times x plus c, and ideally maybe that all equals 0, whatever, I don't, yeah. Just assume that this also says it equals 0, right? Later on, it might be a little more rigorous. Anyway, I wrote this a few days ago, so we'll see. I'll just make it now. Okay, so the equation of the inverse parabola. So that is the opposite part, though what we've shown in other videos. Basically the imaginary parabola, right? Is this, and this guy right here. What this is it is twice the distance, the vertical distance between the y-intercept and the vertex of the parabola. And we need this twice in this case because the y-intercept has to be adjusted by that much, by 2 of them, because you have the distance twice because you have the 2 copies of the parabola. Right? Now, the real complex of the solutions is this. The real part is negative b on 2 all on a. And this is the axis of symmetry of the given parabola, right? So this part here is telling you about your vertical component of the vertex. This part right here is telling you about the horizontal part of the vertex, okay? I mean, it's also always the real component, right? Which is why, if you look at the quadratic formula, the quadratic equation, you get, it starts off with negative b. That's always the real part of the numerator. And then the denominator is 2a. Well, that's exactly what this is. Okay. The imaginary component of the complex solution is all this nonsense. Okay. We're going to get that to be a little bit nicer in a second, right? So here is pretty much what your standard, fairly close, your quadratic equation looks like. So I've put things together a little bit. What I've done is I've taken this. It is here, sort of. The on A is in there. It's handled in there. Yeah. Basically, we got an a squared, so that puts an a on this c, and that when we take the square root, that leaves an a on the outside. And because this b on 2 is squared, you end up with a 2 escaping in the denominator. So, yeah. Or you can just keep the b on 2 altogether, and there's a reason that you would do this. Okay, so the vertex of the given parabola is of the form, the real component is the x. So you got this guy. And then the other part is of this form. So it's something over a. And that's literally why I use the letter s, because something. At this point, it's something. Okay. Your complex zeros look like this. Okay, and there's your real component. Now this guy, this is the vertical distance from the y-intercept to the vertex, as I already mentioned. Okay, so s on a is all this stuff, which when you play with that a little bit, it starts to look familiar. Boom. 4ac minus b squared all on 4a. And then when you take the square root of that, well, you take the square root of that. So that 4 is actually tied to the b. That 4 and that 4 are the same 4. And that 4 on the AC, so notice the signs are different. It doesn't matter. That's what that's going to do is, because we're talking about this one, it's the one that gives us the imaginaries in the first place, so I'm just working with that directly. It doesn't matter, because when you get a negative inside the square root here, what it does is it just gives you the real solutions, which gives you the roots to this one. Anyway, whoops. Yeah, so that 4, it's actually built into this. It's part of this. It's different from this. Okay, so we can see that the b on 2 is actually integral, right? We end up with a on c minus b on 2 squared all over a, right? So I'm going to rename the denominator of this thing to t for, I don't remember why. Anyway, so let's say we've got, these are your a, b, and c. And then we go through all of this, and it works. It works. It gives us the right values. Okay. Now, it so happens that b on 2, this thing that keeps popping up here, b on 2 is the slope between the vertex and the y-intercept. Right? So, there's a reason that this looks like, well, this whole thing with the negative on it, looks like your real component that's been multiplied by b on 2, because it's exactly what it is. Because your the equation for that line is now going to be y equals x times b on 2 plus c. So your and you have the c there. If you plug in the real component, you get negative quantity b on 2 squared divided by a plus c, which is exactly this. Okay, so that's where that's coming from. Because this is the line that intersects both the vertex and the y-intercept. Okay. Now, say we just take that negative b on 2 thing, and we just set it to be a different variable, right? So now we can see symbolically where it shows up, right? So you get an imaginary component is, we have it's root s on a. I'm using v for square root because it visually looks like it, which is the same as the square root of s on a squared, that quantity. That gives us s is ac minus k squared. S on a squared is c on a minus k on a squared. I'm kind of just playing with stuff at this point, and I'm going to walk through it a little bit. Your real component is k on a. This guy, we're getting close now. We're getting close now. So this is actually our quadratic equation, but what we've done is we now have our real component. See how it's showing up here and inside the imaginary component? Okay, it's going to get a little bit nicer now. Okay, so let's play with this a little bit more. If we play with this a little bit more, we get k's ar, yada yada. And now let's just take, so we've got this c on a component. Let's just take that and set that to some other thing, right? Now we end up with all of your zeros are at this guy, which is your real component plus or minus your imaginary component, which is your c divided by a, right? So now basically what is happening is a is showing up as a denominator on everything, which means that it actually just factors out of the entire equation. Whatever a is, it has actually been artificially multiplied by everything. So we can always just remove it, just divide everything, all of your coefficients by a. So b and c, divide them by a in the first place. Okay, that's one way to look at this. And when you do that, you just straight up get this value, and your real thing is the negative 1/2 of b. Right. So now you've got this. This is more accurately the form that you should be using, right? So if we factor a out of everything, you get just x squared minus 2 times the real component x plus this guy, q, right? So aq is your c, that is your y-intercept, but this part is part of the imaginary, and this part is your real, which is also part of your imaginary, okay? And this, let's see, if you factor out the a, wait, let me make sure I'm doing this right. Okay, this part is the slope. That's, yeah, this part is the slope of the line that connects your vertex to your y-intercept. If you take this whole thing and factor out this, you get, no, that's, wait, factor out this, you get the slope. Factor out, I don't fucking know. Anyway, I'm getting confused by it. But, here, let's just actually just use it, right? Let's find the roots of, and I just made this one up randomly, and I was really impressed with it. So, 3 minus 6 plus 15, I was just typing numbers. It was, I didn't intend to actually make them all multiples of 3. Okay, so, your b is negative 6. So, the real component is come on, let's see. What is your real component? Your real component is this. Okay, so you're taking b, so that's the negative 6, okay, and you are dividing it by 2, so you get negative 2. You're taking the negative of that, which makes it positive 2, and then you're dividing that, let's see, you're dividing that by a, wait, 6, negative 6 divided by 2 is negative 3, the negative of that is positive 3, divide that by a, which is 3, and your real component is then 1. Okay, c is 15, so just divide that by 3, and you get 5. Now, plug that all in. 5 minus 1, because 1 squared is 1, that gives you 4. We're going to take the square root of 4, that's 2. Okay, so now we get, our real component is 1 plus or minus 2i. There you go. And it works with the 6-lobe cone that I've demonstrated. Yeah. So if you're given a form like this, a times x squared plus bx plus c, the real component is negative b on 2a, and the other part of the imaginary component is c on a. So now your zeros are at r plus or minus the imaginary quantity q minus r squared, that quantity we take the square root of. Right? So square root of the quantity q minus r squared. That's your imaginary component. And the reason that we're adding and subtracting this is because they are symmetric around the axis of symmetry of the parabola, because that's how parabolas work, and the real component is the real component because it is the axis of symmetry. So, the imaginaries plot out a parabola that is just an upside down version of the parabola that you can see, that you normally draw. And the reason that we really only draw the one is due to the philosophy underpinning functions. It's just easier that way. And there's some merit to that, but there's also a lot of artificial bullshit that came along with that. And you ultimately, here, you end up with a much cleaner expression for the quadratic formula. Even if we put all these back literally as they are, it's still cleaner. Right, so if I took, okay, so if I just replace this, right, with r, so we get this plus or minus the imaginary component, which is the square root of, we're going to take this, boom, squared, and we're going to take this, whoops, we'll just replace q with this. That's still slightly nicer. That's still very slightly nicer than the quadratic equation that you normally see. And we don't have a random ass 4 over here. Right? And the reason the a is coming out is sort of magic. So when we square this a in the denominator here, it means that this guy has to, in order for this fraction to work, we do that subtraction there. You get an a multiplied top and bottom, which gives you a square a on the bottom. But we're going to leave that a on the top, and now you have a squared a in the denominator. So now the denominator of the whole square root gives you an a in the bottom. So like all of this work has been done for you, but it doesn't make it simpler. It just means you have more to remember. And the same thing is here. This 2 that's in the denominator, it gets squared to a 4. And because it's missing over here, you get a 4 on this c. But now the 2 is in the 2 squared is in the denominator, so the 2 comes out when we take the square root. So you end up with a denominator of 2a. And it is nice that it's the denominator of 2a everywhere. That is true. But it's not simpler, and it doesn't explain any, like, if this is the only form that you've ever seen as the standard form, you don't really understand why any of the parts are doing any of the things that they're doing, right? This is literally the axis of symmetry of the parabola. And it's also here, being squared. It's part of the imaginary too. That's not something that you normally see when you're working with the quadratic equation. So, like, I feel like it's worth noting here that this is how this is working.